All right, so we've learned a lot about integration so far, but we've only been able to do some really simple problems. We haven't been able to do anything, for instance, that was clearly a result of the chain rule because we don't know how to undo that yet. So now we're going to start getting into some more sophisticated ways of integrating functions. And the main tool that we use to integrate things from here through the rest of the year is called Substitution. Let's say for integration. And substitution is used anytime you had a chain rule in the original problem. And that's going to be a big deal for us because if you guys recall, a lot of times when we were taking derivatives, we had the chain rule. You know, like 90% of the time there was some sort of inside function to deal with. So substitution says the integral of f prime of g of x times g prime of x dx can be rewritten by saying that u is g of x and the derivative of u is g prime of x dx. So if you look at this problem, this right here is the definition of the chain rule. So if I have an outside function and an inside function, then to take the derivative of that, I do the derivative of the outside and keep the inside the same. And then I multiply by the derivative of the inside. So this right here, everything that I've written right here is the chain rule. And so what I'm saying is I can take out the inside function right here, that's g of x. And right here, the derivative of g of x, or the derivative of u, is g prime of x. And what I can do is I can rewrite this problem as something that I'm going to integrate in terms of u. So I would say what I'm actually going to integrate here is f prime of u times du. So if I look at this, I have f prime of u, and then the du represents all of this right here, the g prime of x dx. So the integral of f prime of u du is just f of u plus c. And then what we could do is we could take the g of x and plug that back in for the u because we know what u represents. So that would be f of g of x plus c, which is what the function would have been that we did the chain rule on. No, I did not plan that to say fu. That's kind of funny. All right, so this is how we do substitution. Let's go ahead and do a couple examples. So we're going to go ahead and integrate. Example 1 says that we are integrating 2x times the square root of 1 plus x squared dx. So what we're looking for, kind of like up here, is we're looking for some sort of inside function where we can find the derivative outside of that. So if I'm looking for what's on the inside, that would be this part right here. So I'm going to say that my u is 1 plus x squared. And the derivative of u is, derivative of 1 is 0. Derivative of x squared is 2x dx. And if you guys can see, I've got the 2x right there on the outside. So I figured out what my inside is, and the derivative of the inside I can see somewhere on the outside. So I'm going to go ahead and rewrite this problem in terms of integrating a u instead of a x. And so that means I have the square root of u times du. So square root of u is representing this, the square root of 1 plus x squared. The du picks up the 2x and the dx. And so this is my entire problem. So I'm going to go ahead and rewrite this so it's easier for me to integrate. That's u to the 1/2 du. And then I can go ahead and use my integration rules. So 1/2 plus 1 is 3/2. And then I'll go ahead and write that out. So I'm going to flip the 3/2 up. So that's 2/3 u to the 3/2 plus c. And once I've completed my integration, I can go ahead and rewrite this with the u plugged back in. So now we're doing this part right here where I said I integrated this in terms of u and I got my result plus c. And then I take the u and I plug it back in with what I substituted out. So 2/3 u to the 3/2 plus c is going to become 2/3 times 1 plus x squared plus c. Oh, and I forgot my exponent, 3/2. And of course, we have it written like this, but we could also rewrite it as a radical as well if we needed to. But for now, we'll just kind of leave it like this unless we can see a multiple choice problem where rewriting it is necessary. Okay, problem 2. We have x to the 3rd times cos of x to the 4th plus 2 dx. So again, I'm looking to recognize an inside and an outside function. So I can see that the inside would be what I'm taking the cos of, and that inside function is x to the 4th plus 2. And that means that the derivative of x to the 4th plus 2 would be 4x to the 3rd plus 0 dx. And I can see the x to the 3rd, but I can't see the 4. So that means that I need to get rid of that 4, and I'm going to do that by dividing by 4 on each side. So that means that du over 4 is x to the 3rd dx. So this time, when I rewrite this problem in terms of u, I'm going to have to keep in mind that x to the 3rd and dx are represented by du over 4. So I've got the integral of cos of u, and so that takes care of this, cos of u. And then for the x to the 3rd and the dx, I'm going to write du divided by 4. Now, most of us would not leave du divided by 4. That's kind of weird. So what I'm going to do is I'm going to say that I have this whole thing is being divided by 4. Like, really, I could extend this line over here. And if I have something divided by 4, that's really like taking 1/4 of that something. So what I'm going to do is I'm going to pull a 1/4 to the front of this integral. So I have 1/4 times cos of u du. And now I can go ahead and integrate like normal. So if I think about the antiderivative of cos, like what function goes to cos, that would be just sine. And so this is going to become 1/4 sine u plus c. And now that I've done the antiderivative, I can go ahead and substitute back in for that u. So 1/4 sine of x to the 4th plus 2 plus c. And if you're ever wondering about your answer, you want to see if it's right, all you have to do is take this and do the derivative of it, which we're a lot better at this point anyway, and then check and make sure it does match this part up here. All right, problem 3. So this one says we're going to integrate the 3rd root of 2x plus 1 dx. And so I'm looking for the inside because that's what my u should be. So here's my inside right here. That's going to be 2x plus 1. And then the derivative of u, derivative of 2x is 2 plus 0, so 2 dx. I don't see a 2 on the outside, so just like before, I'm going to go ahead and divide by 2, because that means I'm not going to take this and replace a 2 dx. I'm going to look at this group and replace just the dx right there. So that means that du over 2 equals dx. And now I can go ahead and take those things and substitute them in so that my problem is in terms of u instead of x. So I've got the 3rd root of u right here. So there's my u. I'm taking the 3rd root of u. And instead of writing dx, I'm going to write du divided by 2. So that means that the integral that I'm actually doing, I'm going to take this divide by 2 and pull it out in the front as a coefficient. So I have 1/2 times the integral. And this 3rd root of u, I'm going to go ahead and write as an exponent. So that's u to the 1/3 du. And then I can go ahead and just do my exponent rules with this. So plus 1, 1/3 plus 1 is 4/3, so I'm going to be dividing by 4/3. Sorry, that's so small. And I can go ahead and rewrite this problem. So I've got 1/2 times, I'll flip that up to the top, so 3/4 u to the 4/3 plus c. And so this is going to be 3/8 u to the 4/3 plus c. And now I can go ahead and plug stuff back in for u. So that's going to be 3/8 times 2x plus 1 to the 4/3 plus c. Okay, and I'm going to do 2 more problems. Yeah, I'll go ahead and do 2 more problems, and then I'll leave the rest for in class so that we can talk more about them if we need to. So example 4 is going to be a definite integral, so from 1 to 2 of 1 divided by 3 minus 5x squared dx. So I'm going to look for my inside function. So u is 3 minus 5x. The derivative of u, derivative of 3 is 0. Derivative of negative 5x is negative 5 dx. Just like the last couple problems, I don't see that derivative anywhere in here. And so that means I need to divide the negative 5 over. So du divided by negative 5 is what will represent the dx. And so now I can go ahead and start rewriting this integral. I'm going to ignore the 1 and the 2 for now. I'll deal with those in a second. So I've got 1 over u squared times du divided by negative 5. So the 1 over u squared is this part right here, 1 over u squared, and then the dx is being represented by du over negative 5. So for me to integrate this problem, I can go ahead and pull out the negative 1/5. And I've got u to the negative 2 du. Okay, so now I have to deal with the definite part of the definite integral, the 1 and the 2. These are in terms of x, and I don't want to put 1 and 2 down here because this part down here is in terms of u. So if I put that 1 and 2, I'm mathematically incorrect. So what I'm going to do is I'm going to rewrite this problem with these numbers in terms of u. So that means I need to figure out what u of 2 is. So if I plug 2 in for x, what would that number be in terms of u? So that's 3 minus 10, which is negative 7. And I need to know what u of 1 is. So 3 minus 5 times 1, 3 minus 5 is negative 2. So instead of saying the integral is from 1 to 2, instead of saying 1 to 2, I'm going to say negative 2 to negative 7. And it is not my job to put these from smallest to biggest for my lower bound and upper bound. I keep the numbers in the same place where they correspond. So the 1 became negative 2, the 2 became negative 7. It's okay that they're kind of backwards. The problem will work itself out, so I don't have to worry about them being bigger or smaller. So now I can go ahead and use my rules. I'm going to add 1 to the exponent, so negative 2 plus 1 means I'm dividing by negative 1. So that means I've got negative 1/5 u to the negative 1 divided by negative 1, and that's going to be evaluated from negative 2 to negative 7. So I can go ahead and simplify this a little bit. Negative 1/5 divided by negative 1 is just positive 1/5. U to the negative 1 should be on the bottom of the fraction. And we're evaluating that from negative 2 to negative 7. So what that means is I have 1 over 5 times negative 7 minus 1 over 5 times negative 2, which is 1 over negative 35 minus 1 over negative 10. And if I do that subtraction, I end up getting 1/14. You could do it by hand. I went ahead and used my calculator. All right, now I'm going to show you, when I did this last year, I showed my students, nope, that's me doing it correctly. I showed my students how to do it, you can see right here I had them do it in terms of u, like this, and I had them just not fix it. I had them like write it in terms of u and then do it back in terms of x, and then use the 1 and the 2. And so if you're comfortable with that, you can certainly do that. Say like, okay, it's u substitution, I'm working in terms of u, and then I'll go ahead and put the problem back in x and plug in just 1 and 2 like I normally would have. However, I realized I had made a mistake at the end of the year when we were studying for the AP exam, because some of the AP exam questions were written in such a way that you had to do it this way, and my students didn't know how to do it this way. So I'm going to be consistent in having you guys translate everything into u's whenever we do the u substitution with a definite integral. But just know this is not the only way to do it. So if you are more comfortable sometimes dealing with only the x value and keeping the 1 and the 2, and you want to evaluate the problem when you've plugged the x's back in, you can still do it that way. It's just the AP exam isn't always, you know, set up the way we want it to be set up. Okay, I'm going to do one more problem, and then we will call it good for the video. So we're going to go ahead and do the definite integral from 0 to pi fourths of sine of 2x dx. So I'm going to look for my inside function, which would be the 2x. And then I'm going to go ahead and take the derivative of that. So the derivative of u would be 2 dx. I don't see a 2 outside, so I'm going to go ahead and divide by 2. So I'm integrating sine of u, and then instead of dx, I have du over 2. So that means that what I'm integrating is 1/2 of sine u du. All right, then I have to consider what my interval should be. So I have u of pi fourths, and I have u of 0. So that's 2 times pi fourths and 2 times 0. 2 times pi fourths would be 2 pi divided by 4, and 2 pi divided by 4 would be pi halves, and then 2 times 0 is still 0. So our interval is going to be from 0 to pi over 2. Okay, so now we're ready to take the antiderivative of this, or to integrate this. And so when I do that, I get 1/2, and then the antiderivative of sine is negative cos. Yep, okay, and then we have from pi halves to 0, and so really I'm going to think of this as negative 1/2 cos from pi halves to 0. So I've got negative 1/2 cos of pi halves minus negative 1/2 cos of 0. So cos of pi halves is actually 0, so that's 0. Minus minus makes a plus. 1/2 times cos of 0 is just 1. So 0 plus 1/2 times 1 is just 1/2.